We all know the sound, right? That steady thump-thump of a heartbeat. But what if we could actually read its story? Well, today, that's exactly what we're going to do. We're going to see how we can teach a computer to understand the heart's electrical language using just a bit of Python code. You've seen this line your whole life, right? In every hospital movie, on every medical show, that iconic squiggly line. It's basically the universal symbol for this person is alive. And for, like, ever, it's been something only doctors and nurses could really decipher. But here's the thing. That's not just some random squiggle. No way. It's actually a super detailed electrical story. It has a beginning, a middle, and an end, and it repeats over and over with every single beat. Every little up and down on that curve means something specific. And that's our mission today. We're going to teach a computer how to read that story. Okay, so the heart's electrical story, what secrets are hidden in the noise? You see, before we can find the story, we've got to deal with the raw manuscript. And when you look at an electrocardiogram, an EKG, as just pure data, well, it's kind of tough to see where to even start. So check this out. This is our starting point. What you're looking at is 5 times full minutes of EKG data from one person. And yeah, it just looks like a big blue blob, right? It's less story and more chaotic ink spill. The secrets are definitely in there, but man, they are buried deep inside all that noise. So how do we even begin to find meaning in this mess? Well, you do it the same way you'd read a book. You start with a single word. And for us, that word is one individual heartbeat. Let's zoom in and see what we can find. Okay, so we're zooming in. Instead of 5 minutes, let's just look at 3 seconds of data. And whoa, look at that. The chaos starts to disappear, and a pattern emerges. All of a sudden, that big blue blob becomes something you can actually recognize. We can now clearly see what looks like, 5 distinct heartbeats, and they all have a pretty similar shape. And now, let's go even deeper. Let's zoom in and isolate just one of those. This right here, this is the fundamental unit of our story. One single heartbeat. But believe me, this isn't just a squiggle. It represents a whole sequence of biological events. Okay, so in the medical world, this whole thing is called a QRS complex. It's kind of a weird name because it's actually more than just Q, R, and S. Think of it like an alphabet for the heartbeat. You've got these distinct electrical waves, P, Q, R, S, and T. And let me tell you, every single one of these little bumps and spikes is absolutely critical. So what do all these letters actually mean? Well, they map directly to what your heart is physically doing. That first little bump, the P wave, that's the spark. It's the heart's natural pacemaker firing up, making the atria contract. Then you get the giant spike, the QRS part. That's the main event. The powerful ventricles are squeezing, pumping blood out to your entire body. I mean, that's why that R wave is so huge. And that final T wave? That's just the heart's electrical system hitting the reset button, getting ready to do it all over again. Okay, so this is why being able to read this alphabet is so important. A healthy heart has this really clean, predictable rhythm. But with something like an arrhythmia, which is just an irregular heartbeat, that beautiful pattern gets broken. You might get missing waves or extra ones or waves that just look wrong. And the data we're actually using for this comes from a famous MIT dataset that's packed with these kinds of medically important irregularities. Okay, next section, teaching a computer to see. So we get the story now, right? We know what a heartbeat is telling us, but how in the world do we get a computer to understand it? The whole goal here is to take what a trained doctor or a nurse does just by looking at it and automate that. Yeah, this quote from the source material just hits the nail on the head. Take what doctors and nurses and paramedics do when they look at an EKG and translate that into code. That's it right there. We're not trying to reinvent the wheel. We're simply trying to capture decades of human expertise and, write it down in a language the computer can understand. And really, the whole process breaks down into 4 pretty simple steps. First, you load the signal. You get the data. Second, you plot it so you can actually see what you're working with. Third, you define the pattern you're looking for, say a specific wave. And then step 4, you just tell the computer, go find it. All right, finding the R wave. So where do we even begin this search? Well, you start with the most obvious landmark in the entire signal, that massive R wave. It's the highest peak by far, which makes it the easiest thing to identify. So here's the big question. How do we teach a computer to find this? I mean, this is the real technical challenge, right? The signal has thousands of tiny little bumps and jagged edges. How do we tell the computer to only find the 5 real peaks that are the R waves? and to just ignore everything else. And the solution? Well, it's actually beautifully simple. You don't need some super complex algorithm. All you need is one simple rule. You just tell the program, find any peak as long as it's above a certain height. That's it. Because the R wave is always the tallest part of the signal, this one rule basically filters out all the other noise for us. So, we run our code on that 3-second sample using just that one simple rule. And the number it gives us back is 5. Remember that 3-second plot we were looking at? We counted 5 heartbeats, and the code, it found every single one of them. It correctly identified the location of each R wave peak. It actually worked. And this is just brilliant. This is the visual proof. We took the results from the code and plotted them right on top of our graph. Each of those little X's marks an R wave that the computer found. It's like the computer has now seen the heartbeats. We've done it. We've successfully translated what a human sees into code that actually works. So, the future of heartbeats. What can this powerful analysis unlock for us? Look, finding the R wave is really just the first step, but it is without a doubt the most important one. Because once you can reliably find every single heartbeat, you basically unlock a whole new world of powerful analysis. Think about it. With this simple foundation, now you can calculate a super precise heart rate just by measuring the time between those R waves. You can automatically detect if a beat was missed, you can identify all sorts of irregular rhythms, you can even start to characterize different types of arrhythmia, all of which paves the way for automated diagnostics that are faster and more accessible for everyone. It's pretty amazing, right? What started with just a simple rule to find a peak can grow into this incredibly sophisticated tool for understanding our health. And it really makes you wonder, if code can read a heartbeat today, what other biological stories will it tell us tomorrow? I mean, from brain waves to muscle signals, our bodies are just full of these electrical stories waiting to be read. So what are we going to decode next?